Welcome to this episode of Numbers in Medicine. Today we're going to talk about calculating a free water deficit and how to derive that equation. The first question really to be asked is, what is a free water deficit? It's defined as the amount of water replacement needed to correct hypernatremia. And truly when people talk about free water deficit, they are almost exclusively talking about sodium. So how to correct a high serum sodium. The free water deficit equation that you'll find online will be some variation of the following. Free water deficit equals the total body water times the quantity, the current concentration of sodium divided by the ideal concentration of sodium minus 1. Now let's dig a little bit deeper into how that equation comes about. So with the basics, concentration is mass divided by volume. But when we talk about electrolytes, they really quantify it in terms of milliequivalents, so really just using its molecular weight to go from mass to this milliequivalence, but ultimately we'll just redefine it as concentration is milliequivalents divided by volume. So for sodium, we can say that the current concentration of sodium is equal to the current milliequivalents of sodium divided by the current volume. So that leads us then to that same equation, that current concentration of sodium equals milliequivalents of sodium currently divided by the current volume. Now to go from a current serum sodium level to an ideal concentration of sodium, we're not going to change the actual amount of sodium. We're not adding or subtracting sodium, but rather we're reducing or decreasing the concentration of sodium by adding water, hence free water deficit. So we can actually redefine the ideal concentration of sodium as the current milliequivalents of sodium divided by this new total volume, which is the current volume plus however much water we add, the free water deficit. So using this same equation, this ideal concentration of sodium is equal to the milliequivalents of sodium currently divided by the quantity, the current volume plus this free water deficit, we can use some algebra just to rearrange the equation. So we'll take the volume plus the free water deficit onto the left side. We'll go ahead and divide by the ideal concentration of sodium, and we'll subtract the current volume to finally isolate our free water deficit, equal to the current milliequivalents of sodium divided by the ideal concentration of sodium minus the current volume. Now this is where things get a little bit more interesting. We have this equation, but we also know that the milliequivalents of sodium currently is equal to the concentration of sodium currently times the current volume. We showed that very early on when we talked about basics of concentration. So if we simply substitute this new term, the concentration of sodium times the volume, in for the milliequivalents of sodium, we get this new equation. Free water deficit equals the current concentration of sodium times the current volume divided by the ideal concentration of sodium, that whole thing minus current volume. We can simply take out the current volume, and then we'll get this final new equation. Free water deficit equals the current volume times the quantity current concentration of sodium divided by ideal concentration of sodium, all of that minus 1. Elsewhere, you'll see this current volume just talked about as total body water. So really, it's the same exact equation. But really, the ideal concentration of sodium is typically 140 milliequivalents per liter. And total body water can really be rewritten as your total weight times whatever fraction of that is water. Classically, we're just taught to think 60%, but there are certain corrections that I'll show you. So we simply institute those new variables. And when we talk about this water fraction, in adult men, it's 0.6 or 60%. In adult women and elderly men, it's 0.5 or 50%. And in elderly women, it's classically 45% or 0.45. Might not be too terribly significant theoretically, but practically, going from 60% to 45% is a 25% decrease. So instead of giving someone 4 liters, you'd actually give them 3 liters. So practically can be very important. Now let's go ahead and do a question. We have a 70 kilogram adult woman with a current serum sodium concentration of 154 milliequivalents per liter, elevated. The question is, how much free water should she receive to have a sodium concentration of 140 milliequivalents per liter? Now, this is the equation we derived. Her free water deficit is equal to weight times water fraction times the quantity current concentration of sodium over 140 minus 1. She's 70 kilograms. We established that an adult woman's water fraction is typically 0.5. And then we substitute her serum concentration of sodium for 154. And we do that math and it turns out to be 3.5 kilograms or 3.5 liters. So she should get 3.5 liters in order to bring her sodium level down from 154 to 140. Now don't do it all at once. There are certain rates that you should be using, but for now let's just focus on determining that total free water deficit. And that is free water deficit in a nutshell.